Hello and welcome back to our complete road design in Civil 3D tutorial series. In this video, we'll discuss how to create assemblies for an urban highway with a link road. This first assembly is for the main alignment and it has a depressed median as a separator. We'll copy the full Road 1 assembly to define the intersection assembly that will be used at the corridor region for the intersection in the next video. After that, we'll define Road 2 assembly with values for the cross-sections from the road design manual. Using Road 2 subassemblies details, we'll define the curb return assemblies for the left and right sides that will be used at the intersection. In case you are watching this channel for the first time, please take a second or two, click that subscribe button so that when I produce a video like this, YouTube will automatically notify you. And to the subscribers, I want to thank you all for the continued support because without that support, this channel cannot be where it is. Let's get started. From the road manual, we have the basic cross-section components of a road design given in Figure 4-1. The lane crossfall slope of 2.5% down runs perpendicular to the direction of travel. An assembly marker splits the cross-section to have the right and left sides, and this is the starting point of an assembly creation. We'll utilize this cross-section for Road 2 design as it contains an undivided crown road. Our sub-assemblies parameters will be from this road manual. After defining the right and left shoulders, we'll add a VERGE, then conditional cut or fill daylights to have the assembly linked to the existing ground surface. At the cut areas, we'll utilize a side drain that will prevent stormwater getting to the road. The end condition for the fill areas will be as seen in the left and cut at the right side. The shoulder is the portion of the roadway next to and immediately connected to the carriageway. Table 4-3 provides us with the recommended width of shoulders for various road categories. We'll utilize a width of 2 meters for the primary road, then 1.5 for the secondary road in our design. A crossfall of 4% is recommended to drain carriageway surface water rapidly. The shoulder on the high and low sides must maintain the same crossfall of 4% on super elevated road sections. You can set your material crossfall as stated in your road manual. We'll use other cross-section sub-assemblies in the upcoming videos. The median is the total area between the outer edges of the outer traffic lanes of a divided road and includes the outer shoulders and central islands. Road 1 assembly will have a depressed median and this other is a raised median that can be used in urban roads. Figure 4-13 provides us with the typical cross-section applicable to our selected design standard. We'll have a depressed median with the inner shoulders provided. Each side of the road section will have 2 lanes, followed by the outer shoulders at both sides. We'll then provide daylights to link the road to the existing ground surface. I will switch to the next document to show you the parameters values. This document contains the design standards that has the summary of our assembly cross-sections that we'll utilize when defining our assemblies. Road 1 will have dual lanes, each side having 2 lanes of 3.65 meter width. Our outer shoulder width will be 2 meters as defined. We'll improvise a median shoulder in our assembly, then use a crossfall slope of 2.5% at the travel lanes. This assembly will have a depressed median and we are going to set all necessary parameters in this video, so watch till the end. The cut and fill ratios will be as given in the slopes detail when we'll be inputting our conditional daylights at the end of the shoulder to define how the corridor interacts with the existing ground surface. The new grade check defined in the previous video has the maximum and minimum grades as given from the manual values here. We can go to Civil 3D to start defining our road assemblies for this road design. The assembly acts as a template for cross-sectional elements. Drop here, then select Create Assembly. Set the assembly name from this line here. I will type Road 1 Full Assembly. From the assembly type, I will drop then set to Divided Planar Road, as we'll be having a median separating the travel lanes. You can select an assembly style or click here to edit an existing style. Set the code set style, then press OK. Click in the model space to specify the assembly baseline location. We'll use the tool palettes to define the various subassemblies elements for our design. You can activate your tool palettes from this icon if you cannot see it in your screen. Go to Tool Palettes, then click on Median tab to select the Median Depressed Shoulder Extended Subassembly from here. Select the assembly baseline to attach the depressed median. This median provides drainage and separates traffic directions. I have offset labels from the assembly style provided in the template. You can reduce the scale to have the offset labels scaled down. The Subassembly Help feature in Civil 3D is a valuable resource for understanding the parameters of any subassembly. Right-click on a subassembly, then select Subassembly Help to view the naming and functions descriptions for the various parameters, attachment, point, links, and shape codes definitions for the selected subassembly. The coding diagram can be located at the bottom of the Help tab. You can select the subassembly, then go to Subassembly Properties from here. Then go to Parameters tab. We can set our input values for the depressed median from here. I will set the ditch width to 0.9. Then set the ditch slope to 3. I will leave as whole ditch slopes. Shift ditch from center. You can set the centerline pivot parameter for the subassembly from here. I will use the direction as away from crown. Then set the left and right median width to 7 meters to have a 14-meter clearance between the lanes. You can set the value for your inner shoulder width from here. I will set to 1.5. You can set the extensions of the layers, and you can view these codes from the Subassembly Help. Look for the cross-sectional details for your pavement structure in your design manual for your layers thickness values. Pave 1 represents the surface course, and Pave 2 is for the binder course. We shall input these values using the basic thickness depth for each layer of the pavement. I will set Pave 1 depth to 0.05, then set Pave 2 to 0.1 and 0.15 for the base depth. We can use a subbase value of 0.3. Hit Apply, then OK. The median now has the parameters we've set from the subassembly properties. We can add a lane to the right side to define the travel path. Go to Lanes tab, then select Lane Super Elevation A or R. Before placing your lanes at the assembly, go to Properties tab, then ensure to set the correct side that you are placing from here. I will set the side to right, then place my subassembly at the right side of the assembly baseline. Zoom to the shoulder, then click on the top point circle to add the right lane. Select the lane subassembly, then go to Subassembly Properties to edit the lane properties. Go to Parameters tab to define the input values. Set the side to right when placing the right lane. Then we can set the width to 7.3. This will cater for the two lanes, each having 3.65 meter width at the right side of the assembly baseline. We can set the crossfall slope to -2.5 as defined. We can repeat the previous values for the pavement layers as defined in the depressed median shoulder to have a uniform thickness. Go to use super elevation, then click. Drop here, then set the side if you have super elevation defined for the horizontal alignment. Inner lane refers to the lane closer to the center line or median, and outer is for the lane further from the median. Set the slope direction to away from crown. I will leave as yes to show you in the model space. Hit apply, then OK to proceed. These yellow icons appear when potential pivot is selected at a lane. I will set the potential pivot to no from the Subassemblies properties. Select the lane, then go to Subassemblies properties. Set the potential pivot value to no. Hit OK. Apply, then OK. We now have the right lane with the correct parameters values. We can mirror this lane to the other side by selecting on it, then use the mirror command from here. Zoom at the left median shoulder, then click on the top point circle to mirror the lane. With this lane being at the left side of the assembly baseline, you can select on it, then go to Subassemblies properties. The side is at the left, but you need to edit the super elevation if present in your design to match the left. The other parameters are okay for this left lane. Hit OK to proceed. We can attach the shoulders to the outer edges of the lanes. Go to Shoulder tab, then select Shoulder Extend All. Zoom to the edge of the lane, then click on the top red circle to add the shoulder to the right side. The thickness is not uniform because of the shoulder parameters. Select the shoulder, then go to Subassembly Properties. Click on Parameters tab. We can edit the input values for the shoulder from here. I will set the width to 2 meters. Then click on Use Super Elevation and drop here to select the shoulder side. This will be our right outer shoulder. I will press OK to proceed. I will set the shoulder slope to -4% as recommended from the manual. For the subbase daylight type, I will set to hold with adjust slope, then press OK. I will give a daylight slope of 3, then set the width to 1 meter. I will leave as no, then give a subbase slope of -2.5%. I will set all pavement layers to match the previous value so as to have a uniform cross-section. Hit apply, then OK to proceed. Our lane and shoulder materials thickness match as defined earlier. We can now add daylights after the shoulder, and you can always check the daylight point from the subassembly help. Select, then go to Subassembly Properties. Pick this icon to open the help dialog. I will scroll down to the coding diagram to view the point details. P2 is above here and P10 is where you should attach the daylight to. Scroll up to view the point's description for the subassembly. P10 is the subbase daylight point as seen from the description, and P2 represents the edge of paved shoulder. Adjusting the shoulder slope ensures water drains effectively without eroding the pavement. Go to Tool Palettes, Conditional tab, then select Conditional Cut or Fill. In Properties, I have right side and cut as type from the parameters. Select this last marker to place. We can edit the display by extending the value of the layout label. I will set the layout width to 10 meters from here, then hit enter. Use the previous command to add the fill condition. Select Conditional Cut or Fill. Go to Properties, then set the type to fill from here first. Adjust the layout width to 10. Then zoom at the last marker and click to attach the fill condition subassembly to the outer edge of the shoulder. Civil 3D will automatically place a cut or fill section depending on the design profile and existing ground surface profile. From the basic cross-section in the design manual, we have a shoulder at the right side followed by a verge, and this is for cut conditions as defined with the natural surface profile. We'll then add a ditch for the table drain, then finish with standard daylights. The left shows the fill condition section. We can proceed by adding the link for the verge at the cut and fill markers. Go to Tool Palettes, place your cursor here, then right-click, select Generic. Select Link Width and Slope Subassembly. Then zoom to your model space and pick the cut marker. We can edit the link parameters by selecting on it, then go to Subassembly Properties. The side is at the right, which is okay. We can give a width value of 0.75 as defined from the manual. I will leave here as no, then use away from crown as slope direction. I will give a slope of -4% as recommended. Hit apply, then OK. We can copy this link to the fill conditional subassembly by using the copy command from here. Then select on the fill marker to add the link with the same parameters. This verge will be added after the shoulder at both cut or fill conditions as defined in our assembly details. At the cut sections, we can add a ditch subassembly by going to Tool Palettes, then Trench Pipes tab and select Ditch from here. Select the outer link marker to attach the ditch. Before discussing on the ditch parameters, kindly take a second or two. Give this video a thumbs up if you are finding this video helpful, and kindly subscribe for more Civil 3D content. Select the ditch, then Subassembly Properties to edit the ditch parameters. You can use the Subassembly help to view the codes used in the ditch. I will leave side as right. Then click here, drop and set to cut to have this ditch included at the cut sections only. We can proceed to edit the other values as per the manual. I will set the ditch width to 0.75. Then set the depth to 0.5. I will set the force slope to 1, buffer width as 1, and buffer slope as -50. You can input the same values for the back slope. Then set the buffer slope to have a positive value from the force slope buffer slope. I will leave the rest as default. Hit apply, then OK. The ditch has been defined with our given parameters values and it has been attached to the verge at the cut condition. You can use the subassembly help to identify the codes used to create any assembly within Civil 3D. After verge, then ditch, we can add a daylight bench at the outer edge point. Go to Daylight tab, then select Daylight Bench Subassembly. Then pick this ditch point to add the daylight. This will link the ditch to the existing ground and creates benched or stepped slopes to stabilize cuts or fills. We can use the subassembly properties to edit its input values. I will set my cut slope to 1.5, max cut height to 5, fill slope to 1.8 and max fill height to 5. I will then set the bench width to 1 and bench slope to 2.5. You can proceed to edit the materials for your design. Hit apply, then OK. Select the daylight bench. Then use the copy subassembly command and place it after the verge at the fill condition outer edge marker. I will highlight all subassemblies to the right up to the shoulder, then use the mirror command to mirror to the left side. Select the mirror command from here. Then zoom to the left lane and pick the edge of travel waypoint. We have created the full Road 1 assembly as defined from the design standards in the manual. After you mirror your lanes and shoulders, it is important to go to Subassembly properties and adjust the side of the super elevation slope if used in your design. I will click here, then set to left outside shoulder as the super elevation slope. Hit apply, then OK. The side of the mirrored elements are automatically adjusted and the other parameters will be the same for values such as slopes and pavement layer thickness. We can highlight Road 1 full assembly. Then type CO, then enter to activate copy command. Click to specify the copy base point. Then click again to place the copy. We'll edit the name of this copied assembly to Road 1 intersection from the toolspace palette. Right-click, then select Properties. I will edit the name to Road 1 intersection assembly. Hit apply, then OK. We'll edit the subassemblies for the intersection ahead in the next video when defining the corridor targets for a comprehensive understanding. We can create a new assembly for Road 2 full assembly, then edit the name in this field. I will set the type to undivided crowned road, then press OK. Click to place the assembly baseline. I will highlight on the right subassemblies up to the travel lane to copy them with the previously defined parameters to Road 2 assembly. Select Copy from here, then select Road 2 full assembly marker. I will select on this lane, then go to Properties palette. Road 2 will have a 3.65 meter width. This assembly consists of a lane, shoulder, then daylights at both ends. Highlight every subassembly to the right, then use the mirror command and select on the assembly baseline marker. We can adjust the parameters of the super elevation for this left lane. The side is set to left, but we need to change to left lane inside, then hit OK to proceed. I will select this lane, then select the subassembly properties to edit the super elevation from here. I will set to left outer shoulder, then hit OK to update. This lane is adjacent to the assembly baseline and it should have the left inner lane parameter. I will set the super elevation input value to left lane inside. Then hit OK, then apply to update the subassembly. Select the right lane, then go to subassembly properties. Set this lane to right lane inside, then hit OK. We now have Road 2 full assembly defined and we can proceed to create the curb return assemblies for the intersection design. I will name to left curb assembly, then press OK with type as undivided crowned road. Click on the model space to specify the location of the assembly baseline. The curb return assembly for the left side will have a lane to its right and a shoulder to its left. The curb return baseline will be located between the shoulder and the lane here. and we'll need to set the lane slope to the positive value for the lane at the curb return. Select the left shoulder, then select Copy Subassembly command and pick on the created left curb assembly baseline. Select the right lane from Road to Full Assembly, then select the Copy command and pick the left curb assembly baseline. Select the right lane, then go to Properties palette. Set the default slope to a positive value from the defined full road assembly. We'll use this assembly to define our corridor targets in the next video. Highlight on the left daylights, then select Copy Subassembly command. Select the shoulder daylight point to copy the daylights to the left curb assembly. We can create the right curb return assembly for the intersection design. Click here, then select Create Assembly. Edit the name to right curb, then press OK to proceed with the previous assembly type and style settings. Click in the model space to place the assembly baseline. For the right curb return baseline, it will be located between the right lane and shoulder, and the lane slope will need to be set to a positive value at the intersection. We can highlight the right daylights and shoulder, then select Copy Subassembly and pick the right curb assembly baseline. Select the left lane, then copy it to the right curb assembly baseline. We can adjust the default slope lane value from the Properties palette to a positive value, then hit Enter. Copying an existing defined subassembly quickly helps to duplicate to a new assembly with the parameters, and we now have all assemblies required for this design. The assembly style used has offset labels defined at the edge of our subassemblies. Our required left offsets for the left side is -7 and -14.3, which represents our lane offsets from the assembly baseline. Our previously defined offsets represents the edge of travelway, which was supposed to be set at plus and minus 14.3 for Road 1 alignment. In Road 2 full assembly, the offset is at plus and minus 3.65, which matches our previously defined offsets. Select an offset, then select alignment properties to view the offset parameters. This offset is at 3.65 from Road 2 alignment. I will select this left offset, then select alignment properties and edit the offset value to -14.3 to match our assembly offset label value. The connected alignments will automatically adjust with the new defined offset value. All profiles associated with these offsets are automatically updated if you have dynamic update option selected. We can also set the right offset value to match our assembly offset label, then hit OK to proceed. The alignment offsets will represent the edge of travelway in this design. We now have all the required assemblies for our corridor modeling, which will be the next video after this. I will briefly explain a crucial detail before ending this video using this assembly. The right side contains assembly details for a divided ground road type. This lane, which is closer to the median, is defined as the right inner lane and this other the right outer lane. The left side contains assembly details for a divided planar road type. The left offset is at -14.3 and this side has been defined with a single lane. The right side offset has two lengths and represents a divided ground road. We can preview the roadway type from the Create Super Elevation dialog for a clear understanding. An undivided crown roadway is a single carriageway with the crown at the center sloping outward at both sides. An undivided planar has a uniform planar slope across its width sloping to one direction. A divided planar road with median has two carriageways with each carriageway having a uniform planar slope. A divided crown road has carriageways that each has a crown at its center line as seen from these previews. Each carriageway is independent and separate lengths should therefore be designed if working with the divided crown road type. And that is how you can create assemblies for a road design with two alignments. We've covered the main road assemblies and the curb return details that we'll be using in the next video on the corridor design. If you found this tutorial helpful, kindly give it a like, subscribe for more civil 3D tips, and leave your questions or suggestions in the comments below. Thanks for watching. See you in the next video.